Hello everyone, welcome to my videos on elementary differential equation. This is video number 4 for chapter 4. We now discuss higher order linear differential equations, but non-homogeneous, meaning that the right hand side g of t is not 0. The focus of this video will be on how to find a particular solution. So to begin with, let's talk about the simple case with constant coefficient. So in that case, in the previous videos, we talked about how to find a set of fundamental solutions, y1, yn, and these are functions like exponential, sine, cosine, and combined with polynomial. Okay, and so that is given, and then the right hand side function, the source term g of t, is also a combination of exponential, sine, cosine, and polynomials, and in a similar setting as we did for the second order equations, constant coefficient and non-homogeneous. Okay, so in this case of a higher order situation, we would follow basically and I would say same pattern or very similar pattern as for the second order equations to get the correct form of a particular solution, and then you will fit that form in to find the coefficients as we did for the second order equations. Okay, so I will not go into details of this, I've just mentioned this. Okay, so for the remaining of this video, we will talk about a method called variation of parameters. This is a method we have also encountered for the case of a second order equation in a more general setting, and now we will extend this for higher order equations. Okay, so I put a star here to show that it's a topic that normally might not be covered for a sophomore level course. So watch it if you want as supplementary material. Okay, so here we're considering a more general case, and that means it's not constant coefficient, so we can rewrite the equation into this form, which we call equation A, such that for the highest derivative term we have coefficient 1, and for the lower derivative term we have variable coefficients. These are p I of t, they are functions of t, until the p not t for the y term, and the right hand side g of t is a function. Okay, so not necessarily just exponential or sine, cosine. And now we assume, which is a big assumption, that is for the homogeneous equation, if the right hand side shall be 0, then theoretically we have a set of fundamental solutions, n of them linearly independent. So assume that we have those already, y1, y2 to yn. These are n solutions linearly independent for the homogeneous equation with g equals 0 on the right hand side. So that is the starting point for this method. Once this is given, we will use this information to find a particular solution for the non-homogeneous equation. Okay, so a particular solution, now we seek a particular solution of the following form. So capital Y will equal to, we'll utilize these solutions y1, y2, and yn, and for each of them we multiply them by some function of t. So for y1 is multiplied by u1 of t, and y2 is with u2 of t, and then yn is un of t. Okay, so there are n functions, u1, u2 to un. They are functions of t, and they are to be determined such that we're fitting those functions here such that this capital Y becomes a particular solution for the non-homogeneous equation. Okay, so we see that we have n unknowns, degree of freedom, and then there is one constraint, that is, if you plug in this capital Y here, and this equation must hold. So one constraint for n degrees of freedom, which means we now have n minus 1 free choices to impose as additional constraints on these functions of ui's. Okay, so we want to use these free choices wisely and to construct a way of finding the particular solution. Okay, so let's now go through a little derivation. Okay, so we start with the particular solution, capital Y, is now in this form. That's the form we are seeking the solution. I dropped all the t dependents just to be brief. So all these are functions of t. Okay. We now write out y prime. So we see that each term in y is just a product. So we can apply the product rule. So if we apply the product rule, first differentiate in all the y's and keep the u's, then we get all these terms, right? So, and then there is the set that we differentiate all the u's and not y's. Okay, so the u will be differentiated, u1 prime and u2 prime, and the y's are kept the same. Okay, so if this confuses you, you can think that differentiating this term by product rule, you get two terms. The first is differentiate y1, you get this term, and then the second, u1, you get that term. And the same for this, you differentiate y2, you get this term, and you differentiate u2, you get that term. Okay, so I just write this in this way, that I collect the derivatives on y all here and the derivatives on u all here, and I mark them red. And then we will need to differentiate further. And if one differentiate these terms, you will end up with the u1 double prime, u2 double prime, un double prime somewhere multiplied by y's, and that's undesirable. So remember, we have our n minus 1 free choices, so we're going to use 1. So I color this red. This term in red is set to be 0, so I use 1 constraint now. Okay, so remember, now this is set to be 0. That means y prime only equal to the black terms. Okay, now let's repeat this process to figure out y double prime. So it's a product here. So if I differentiate, I get two terms. One is differentiate on y1, so I get y1 double prime. And the other is differentiate on u1, which is here, u1 prime times y1 prime. And do the same for this derivative. I'll get this term plus that term, and so on and so forth. Okay, so I collect them in a similar way, such that the higher derivatives on y's are here first, and all the terms involving u primes are collected here. And then I know I need to do the third derivative, and I do not wish to differentiate u1 prime again. So all these terms, this term add up, this red term, the sum of all these, I set them to be 0. So that's the second constraint I use. Okay, I think you might see what I'm doing here. You might see the pattern. Okay, so similarly, I write out one more y triple derivative. So now you see the pattern. So this is differentiating all the y terms from here. And this term is 0, so I only get that to differentiate, and then differentiate all the u terms. I collect it here. And then I know that all these red terms shall add up to be 0 again, so I used my third constraint. Okay, so one can continue this process of differentiating and write them into two parts and set one part to be 0, the red part, until you reach the n-1 derivative. Okay, and you do a similar thing. You collect all the derivatives on y's, n-1 derivative, and the other terms in red, and these you set to be 0. So now you see that I have used 1, 2, 3, 4 all the way to n-1. So I have used my n-1 free choices. Okay, so now the last constraint is that capital Y shall satisfy the non-homogeneous equation. So we will plug this back in. So the advantages of this derivation form, you see that all the derivatives will take relatively simple form because all the red terms, they are 0. Okay, so the derivatives from y to all y n-1 derivative, all these terms will exactly contain n terms, and they will all have this simple form. Okay, so before we proceed on that constraint, let's collect the n-1 constraints that we have imposed. So all the red terms are 0, so this is coming from the y prime, and that's y double prime, and so on and so forth, and this is for the y n-1 prime term. Okay, so let's clean up a little bit. We are going to plug in the capital Y into the differential equation. So we see that since all the red terms are now set to be 0, the derivatives of y will have a relatively simple expression. So drop all the red terms. Let's summarize all the derivatives from y prime to y n-1. Okay, they all have n terms, as we have noticed. And now we differentiate this one more time because y to the nth derivative is also needed in the equation. Okay, so then we see that we also have a first part where we differentiate all the y terms, and then we have a second part where we differentiate the u terms. Okay, and then we can now plug all these into the non-homogeneous equation, and what would we get? Okay, so it might be useful to write out the expression of y. What is y? Y is y1 u1 plus y2 u2 plus all the way to yn un. And then we know that the equation for y will be the y term is multiplied by p0 of t, and this one is multiplied by p1, and this is multiplied by p2, and so on and so forth. And then the n-1 of y is multiplied by p(n-1) as a function of t. Okay, and then all these terms will be added up and set to be equal to g of t. Now let's collect like terms. So let's collect terms that involves u1. Which terms have u1? Well, this term has u1. Taking out u1, I get y1 to the nth derivative. And this term has u1. Taking out u1, I get pn-1 times y1 to the n-1 derivative. And all the way, all these first terms will be collected, and then all the way over here. Then if you take out u1, you get p1 y1 prime, and then here if you take out u1, you get y1 times p0, which is here. Okay, and then you do similar thing for u2, which are all these terms, which will give you that, and all the way to un, which are all these terms, which will give you this by taking out the common factor, un. And then what remains are these blue terms. They are not multiplied by anything, so let me just repeat them here. All the blue terms come over here, and then the right hand side is g of t. Okay, so we get this constraint, which currently looks very big, but we'll simplify it. So how do we simplify this expression? Well, remember, what are these little y1, y2 all the way to yn's? We know that they are all of them solution to the homogeneous equation. And look at this expression, and that's exactly the left-hand side of the homogeneous equation. So this means all these red terms, they shall all be 0. The only non-zero term on the left-hand side is this the blue terms in this bracket here. Okay, so we dramatically simplified. So these are gone, we don't have it anymore. And then the constraint is just this one, which I am circling around. So you have that. So that is the last constraint, and we're going to combine it together with the previous n-1 constraints we have derived earlier. Okay, let's collect all the constraints. Now we see that we have n equations and we have n unknowns. The unknowns are the functions u1, u2, un, and u1, u2, un, that's are the unknowns, and the y1, y2, all these y's are actually given. Remember, that's the starting point. Okay? So we see that in this system of n equations, all the u's actually all appear as the first derivative. So we only have u1 prime all here, and u2 prime all here, and un prime all here. So we can treat those as unknowns. Okay, so treating the derivatives of all the ui's as unknowns, we can rewrite it in matrix vector form. It's always useful to do that for linear systems. And then we have the coefficient matrix, which includes just the y's, y1, y2, yn, and the first derivative and second derivative, so on and so forth, to n-1 derivatives. Okay, and these are the unknowns, the ui primes, and then the right hand side are zeros, all zeros except the last term is g of t. Okay, so in favorable situations, we should be able to solve this for all the u1 prime, u2 prime, un prime. So what is the condition that one can solve this? Well, the condition is that this matrix here shall be non-singular, that is, it's invertible, right? So does this look similar? Somewhere we have seen it. So how do you determine if a matrix is non-singular? So one way you can check if this matrix is singular or not is to compute its determinant. If it's not 0, then it's non-singular, and that it's invertible, and then this equation has a unique solution. Okay, so what is the determinant of this matrix? We see that the determinant of this matrix, it looks very similar. In fact, we recognize this as the Wronskian determinant. And is it 0? Well, it depends on if all the y's are linearly independent. And since the starting point is that all these y's are a set of fundamental solutions, which means they are linearly independent, and therefore the Wronskian of this, the determinant of this, is never 0. Therefore, we can solve this system for any given gt to obtain a unique solution for ui primes. And once you have obtained all the derivatives ui prime, then you can integrate to recover the ui's, the coefficients. Okay, so let's end the video with the summary of our findings with the derivation. Okay, so the starting point is we have a set of fundamental solutions for the homogeneous equation. Then with that, then we can find a particular solution for the non-homogeneous equation with gt on the right hand side, which takes the form capital Y is u1t times y1 u2t times y2 add up to unt times yn, and the functions, the variable coefficients u1 u2 will satisfy this linear system where the derivatives can be solved uniquely, and then you will recover the u's by integrating the derivative. Okay, so as you see that this is kind of a very convenient formula to remember for this topic, and it's actually not a bad formula. So you should keep in your mind that the derivatives are the unknowns, and then here the coefficient matrix is just the Wronskian determinant of this matrix. So all the y's are here, y primes are here, and you differentiate one more time all the way until the last row is you differentiate n minus 1 times. Okay, and the right hand side is all 0 except the last one is your gt. So it is quite okay to remember, at least for a short while. Okay, so that's the end of the derivation for this method, and in our next video we will give some examples of how to work it out. Okay, so I hope you enjoyed this video, and I'll see you next time.